Okay, let's continue with our third major topic that we had. Um, Rather, the second one. We've discussed database administration, and now the second major topic among this advanced, more advanced topic is the topic of concurrency. And just to remind ourselves what that is, and I think I drew this little diagram of the database life cycle, and you had the design and implementation in the early phases of the life cycle, and at this point the database is released for use to end users. From here on out to the end of its useful life, that could be many years actually, the database is in operation by hundreds of users. So the issue during operations of a database is that there are hundreds, if not thousands, of users. And actually hundreds of simultaneous users. Okay, and one example, there are lots of examples of these things. One example you can think of is an airline database where thousands of flyers could be potentially searching for fares and making and booking flights at the same time on the airline's database. Okay, so concurrency, it covers lots of technical issues, but the major objective of concurrency is that since you have so many simultaneous users, you have to make sure that one user's work does not inappropriately influence another user's work. What does that mean, and why does this issue even arise? Why could there be an inappropriate influence? What do we mean by inappropriate influence? And in order to understand that, we have to understand the concept of a transaction. A database transaction. Okay, so as humans, we often we think of transactions as things that are one time, or rather a unit of activity. So I'll take a very simple example. A transaction is you want to transfer money from your savings account to your checking account. And let's say you want to transfer $1,000 to you. You are one of the thousands of users who have walked up to an ATM, let's say a Bank of America ATM, and you just want to transfer $1,000 from your saving accounts to your checking account. Okay. Now, to you, this is a transaction. Okay, so for you, this is one unit of activity. You just want to transfer $1,000 from savings to checking. But for the database, this is not one operation. For you, this is one operation. You meaning the end user. But for the database, this is not one operation. Just think of all the little things that have to go on. So you are at your ATM. The first thing you might want to check is your bank balance. So the program, the application program that is showing you the user interface, it goes to the database and fishes out your balance in your savings account. And then you say, type in, I want to transfer $1,000. First, it has to make sure that you have $1,000 in your account, in your savings account. And once it makes sure that it has that $1,000, it subtracts. So it subtracts $1,000 from your savings account. So that's admittedly, on today's computers, these things take very small amounts of time, but they are not instantaneous. They do take some amount of time, and there are thousands of people doing this at the same time. Okay, so the database, the application program deducts $1,000 from your savings account, and it adds $1,000 to your checking account. And so these revised balances, so I'll just call it savings 1, and I'll just call it checking 1. These are the revised balances. They get written back to the database, okay, permanently. So you can see that what looks like one operation to you, one transaction to you, actually consists of a lot of steps. Okay, and stuff happens in the middle of things. Okay, so this might be taking 2 milliseconds. this entire operation might be taking 2 milliseconds. But still, that's an eternity in terms of computing time. So let's say in the middle of this transaction, your communication line crashed. The communication line from the ATM to the database, which is, let's say you are in DC and your database is located in Nebraska. So the communication line crashes. So your transaction, what you thought was one operation, has gotten disrupted in the middle. So you have lost $1,000 from your saving account, but it has not been deposited into your checking account yet. And those operations got disrupted in the middle. So somebody has to make sure to recover from that problem, to recover from that crash. So you can see that unless I take action and take appropriate steps, I can cause problems. I can have inappropriate or inconsistent results in the database. So this is a concept of a transaction. The basic idea you have to remember is what appears to be one operation to you at the end user level, what you think of as a single transaction, is actually a combination of lots of little steps underneath, and things can get disrupted, things can happen in the middle of those steps. Okay. Now, if you take this concept of a transaction and apply it to multiple users, okay, so let's think of this. So you have user 1 and you have user 2, and this time we'll use an airline database example. Okay, you'll see that it's in some ways it's similar to what we did for the checking account. So you have a particular flight, let's say DC to Chicago, and the seat has one empty, the flight has one empty seat left. Okay, so user 1 logs into United's portal and they see one seat left, so they book that seat. User 2, who has logged in at the same time, because the database retrieved this information and gave it to user 2. User 2 also sees one seat left, so he also books the same seat. Now, if the system doesn't do anything special, they have interfered with each other, isn't it? Because this fellow will book one seat and think that he's gotten the seat because the number of empty seats is now 0. The number of empty seats is 0 here. But there was one seat left. You can't have two passengers buying that one seat. Okay. And the reason this inconsistency arose, so one transaction, so what appeared to be one transaction to a user, each of these users actually consists of multiple operations, as you saw. So just like your checking and savings account, the actual steps would be you would read the number of empty seats, and when the end user sees one empty seat left, they book the seat, and this gets reduced by 1 equals empty seats minus 1, and that reduces to 0, and this is written back. So both transactions write back 0. So one overwrites the other. So you don't need to know all the technical details of how that goes on between main memory and your database, which is usually a permanent storage of some kind. But you can easily see that two transactions have interfered with one another. So concurrency control tries to make sure that this kind of interference doesn't happen. Okay, and that is what we were saying, that one user's work, what we meant when we said one user's work does not inappropriately influence another's work. So in order for transactions to work well, to work as intended, you have this concept called ACID, and you said it's a convenient acronym to remember. Transactions should be carried out by the database in such a way that they meet this condition. ACID stands for atomic, consistent, isolated, durable. Atomic means that even though a transaction actually consists of a lot of steps, the way you run it in your database should emulate, even though the actual running of the transaction consists of multiple steps, the effect should be as if it was atomic, as if it was one single operation. That's what we mean by atomic. Okay, and then consistent means that no transactions are permitted on the record until the transaction finishes. Okay, so half-baked results should not be stored in the database. You saw the example in the checking account case where a crash or some sort of abnormality happened in the middle of the transaction, and so that compromised state should not be recorded in the database. So either your transfer from savings to checking would not occur at all, or if it did happen, it must go to completion. Okay, so either nothing got deducted from your savings account, or if $1,000 did get deducted from your savings account, they must show up in your checking account. So either your transaction happened or it didn't happen, happened to completion, or it didn't, as if it never started. Okay, so you have this consistency, and then of course you have these other two characteristics of a transaction. Isolated. So again, this is just a technical definition of isolation. In the multi-user environment, different transactions may be operating on the same data, which can result in continuously changing data element. So this is the example that I gave you of the airline database, where the same record could be accessed by different end users, and you have to make sure that the concurrency mechanisms that you have allow for those two transactions to go on in parallel without ending up with inconsistent final values in the database. Okay, and then you have this characteristic called durable, in which when the database comes back and tells the end user that yes, you have booked a seat, then that result, if it has committed that to the end user, then that result should be reflected in the database as well. Okay, so now let's take a closer look. So this lost update problems, these are examples of what happens if you don't have concurrency control. So the lost update problem is the airline reservation example that I gave you, where there was one empty seat left and two users thought they were booking the same seat. So essentially, the reason that problem arose is that the update by one user, so whichever user got to that seat first, their change was not, so the last user's change is what gets reflected in the database, and one of them, their change got lost. Okay, so the lost update problem. So when two users simultaneously got to that one empty seat, one of them should have been told, hey, another user is working on this seat, you can't have it. Okay, so the update from the first user who was trying to book their seat got lost, and the second user didn't get that signal. Okay, so here are some other problems that can arise. So dirty reads, inconsistent reads, phantom reads. Again, you don't need to know all the really in-depth technical aspects of what these reads are, but the basic idea to get across is, if I don't do concurrency control, I haven't yet told you how concurrency control is done. All I've told you is what is concurrency control. It's a mechanism that is used to make sure that when you have simultaneous operations on the database and each simultaneous transactions, and each transaction consists of several small operations, then we must control those operations in such a way that that ACID characteristic, that abbreviation, those characteristics are maintained, and you don't end up with compromised content in the database. So now let's take a look at how concurrency is achieved. It's achieved by a mechanism called locking. Okay, and essentially this means that before you actually make changes to the database or operate on it, the transaction will lock whatever resources it needs. So again, going back to our airline example that we had, where two end users were trying to book the same seat, what would happen is the first user, before it even started doing all its operations, would lock that seat, lock that record. And so when the second user, even if that second user came a microsecond later and wanted to book that same seat, they would not be able to lock that resource because that record which contains the one empty seat has already been locked by the first user. So locking is a mechanism that's used to achieve concurrency, and but it creates its own problems. You can get into what are called deadlock. Let's see. So deadlock, you can get into a deadlock situation. So let me give you a simple example. So I have user 1 and I have user 2. Okay. So user 1 and user 2 both need two resources. Think of a resource as two records in two different relations in a database. So resource 1 and resource 2. So this is usually some portion of the database. So user 1 and user 2 are working concurrently, and locking will be used to control concurrency. So here's what happens. User 1 needs both R1 and R2. User 2 also needs R1 and R2 to carry out its transaction. So user 1 locks R1 and user 2 says, oh, I can't, R1 is locked, so it says R2 is free, let me lock R2. Okay, so now user 1 is waiting for user 2 to release lock R2 so that it can get it, and user 2 is waiting for user 1 to release R1, the lock on R1, so that it can use it. So you have what is called a deadlock. And this happens not infrequently. So when deadlock happens, the system hangs. So you have two users waiting for each other. And this is a simple form of deadlock. You could have three users, A waiting for B to release something, B waiting for C to release something, and C waiting for A to release a resource. So deadlocks can get pretty complicated, but locking solves one problem and creates another. There are ways to break deadlocks, but for now, for this class, you just need to be aware that that locking is a mechanism that's used to achieve concurrency, but it has its own issues. Okay, so hopefully this gives you an overview. So this tutorial, the main objective was to give you a sense of of multi-users. When you have multiple users working on the database, which is always the case, then how do you make sure that their transactions are consistent, they work as intended? So this whole issue of concurrency, what happens if you don't enforce concurrency control? What are the bad things that can happen? And one particular mechanism that's used to achieve concurrency called locking, and we've just introduced that. So I'll stop this recording for now, and in the last recording we'll talk about the third topic, which is database security, and we have a few words about indexing.